Hello, everyone. This is Jeff Clune. It's a pleasure to be here. I want to thank the organizers for the invitation. Today, I'm going to talk about learning to continually learn. At the highest level, first, what I want to do is talk for a little while about how we might achieve the grandest ambitions of our AI community. We often talk about this over drinks at AI conferences, but not in the research talks themselves. But I actually think it's helpful to think about and be explicit about how might we accomplish the grandest goals of our field. So I'm going to introduce a paradigm called AI generating algorithms, which I've recently introduced that I think might help us get there. And then I'm going to show a style of that paradigm, which is applying that approach to continual learning, specifically trying to solve catastrophic forgetting. And that's going to be the main event of this talk, which is focusing on the ANML algorithm, which we'll get to later. So first of all, if we want to produce artificial general intelligence or human-level AI, we all recognize we have a long way to go. And the question is, how will we get there? We don't often think about that. I think that most people in our community are engaged in what I consider the manual path to AI, which is the dominant paradigm. And that is that we identify each building block to AI, and then we present those at conferences. We either have a new paper that says, here is an improved version of an existing building block, a better architecture, a better normalization scheme, or here is a new building block that no one's ever published on before that I think is going to be important as part of the overall machine. But if you look at kind of the conferences and all the papers that come out and a list of all the building blocks, it begins to dawn on you just quite how daunting of a task this is. How many more building blocks are there out there? Are there hundreds or are there thousands? Are we going to be able to find them all one by one manually? That seems a very, very tough challenge. But even if we were able to do that, this manual path implicitly has these two phases. In the first phase, we find them all. And then in the second phase, we have to take on the Herculean task of combining all of these building blocks together into some giant Rube Goldbergian thinking machine. And I think we should be clear-eyed about how difficult a challenge that is. We're talking about putting together hundreds or thousands of parts that interact in nonlinear ways, each with their own hyperparameters, and debugging that sort of a system is very difficult. And it doesn't jive very well with our scientific community and organization. Instead, it would require a massive CERN-like effort where nobody publishes for quite a long time because we're all putting this machine together. I think, however, that there's a clear trend in machine learning that suggests an alternate path. And that trend is that over time, what we realize is that hand-designed pipelines are ultimately outperformed by learned solutions. And we've seen this time and time again. For example, in deep learning, especially in vision, we used to have manually designed features such as hog and sift, and now we just learn them end to end. That's also applied to many other modalities for deep learning. Architectures, we also have historically mostly hand designed them, but increasingly we're seeing people learning them and producing state-of-the-art results with learned architectures, and I predict that will continue as compute becomes cheaper and as the algorithms become better. We're also seeing hyperparameters and data augmentation switch from being manually set and designed to being learned. And even now, the RL algorithms themselves are being learned with meta-learning. So this, as I mentioned, suggests an alternate path to get to powerful AI, and that is what I call AI generating algorithms. Here, the idea is that we try to get the human out of the way, and we will try to learn as much as possible with machine learning to start one algorithm that bootstraps itself up from simplicity all the way to ultimately producing human-level AI or beyond. The idea is that you have something like an outer loop that's very expensive, that is searching over architectures and algorithms and training environments. But ultimately, what that thing does is it produces a learner that itself is extremely sample efficient at the end of that process. For example, we have an existence proof, which is Earth, which had a very expensive outer loop that ultimately produced the human brain, which was the most impressive, most sample efficient learner that we are aware of. And I think that we are going to end up going down this same path. So to make progress here, we're going to need to push simultaneously on three different pillars. The first is architecture search, where we can meta-learn the architectures. The assumption here is that the transformer is not the last architecture we will see that is powerful. There are other ones out there that we'll want to search for and discover. Second is that we'll meta-learn the learning algorithms themselves. And third is that we'll automatically generate effective training environments in a system that can bootstrap itself up in complexity and doesn't rely on humans to set the next challenge each time. So what I'm going to do quickly is tell you about some work that we have done in our group on each one of these pillars. but I want to say there's been tremendous amounts of work by many in the community on all of these pillars, and increasingly I'm seeing more and more work in these pillars, which I see as kind of a sign that this paradigm is taking off, which is great. So on pillar 1, to meta learn the architectures, one thing that we recently put out are generative teaching networks, which I think are promising. The idea here is that you can accelerate architecture search by synthetically generating data that rapidly trains up any new architecture as quickly as possible to see the potential of that architecture. And then you can use that as a proxy in architecture search to more rapidly do architecture search. There's a blog post about that there. We also recently put out some work called the synthetic petri dish, which I encourage you to check out. This is an idea that you can synthetically learn the training data for a slightly different purpose. Here, the training data are designed to such that when you train little tiny slices of a neural net or motifs of a neural net on this training data, the result is predictive of how those architectures are going to be in the wild. For example, you could learn automatically a training set that is looking for translation invariance. So it could put a pattern in like 3 quadrants of the training set, but never in the 4th quadrant. Then on a synthetically learned validation set, it puts that pattern in the 4th quadrant, and it says, oh, architectures that are, when trained on this training set, actually generalize and recognize that pattern in the 4th quadrant. Those are translation invariant. They've shown the ability to generalize those, much more likely to be good in general in the wild. And therefore, that is a motif that we want to predict will be highly beneficial. And so then when we can launch architecture search, you can find those kinds of motifs like discovering convolution and other types of things that help generalize very well in machine learning. So that's another new technique you might want to look at. For pillar 2, there's been a tremendous amount of great work on meta learning. We're going to return to this subject later. The idea here is you learn the learning algorithm itself, like the work of Jane Wang or RL squared, or the mammal style approaches. Here, what we did is we put out a new material, so like a new building block that you can learn meta learning algorithms with. Specifically differentiable plasticity. These are basically built on Hebbian learning style systems. But here you can now use end-to-end backpropagation to train very large Hebbian learning nets, which is an alternative to classic SGD-based networks. The third pillar is the least investigated and therefore arguably the most important for people to start working on because there's the most low-hanging fruit. It's also going to be essential for these systems to bootstrap themselves up in complexity and take humans out of the loop to really speed things up. And so what you want to do here is you want to kind of generate an increasingly large set of learning challenges for an agent as it gets smarter and smarter and smarter to continuously allow it to learn new skills. So our latest salvo in this line is an algorithm called POET, which is an algorithm that tries to endlessly generate increasingly complex and diverse learning environments and their solutions automatically through this algorithm called the paired open-end trailblazer. It's done with these colleagues here, and there's a blog post about it. And very recently, here you can see the little agent here running through some auto-generated obstacles. Very recently, we put out a new paper called Enhanced POET, which builds upon POET. It provides a new domain general metric of whether an environment is interestingly novel called POTA-EC. It has efficiency improvements. It also has a more open-ended environment encoding, and it provides a domain general measure of progress in open-ended systems, or ANNEX. So here you can kind of see the contrast. On the left was the original POET. On the right, you can see a much more kind of rich, subtle space of possible environments that the POET algorithm learns to solve and generates all by itself. And what you can really see here is the kind of the delta between the two, that even though the original POET was very promising, ultimately it ran out of speed because it kind of maxed out what was possible in that environment for that body. But here, Enhanced POET is really showing its ability to keep going in a more open-ended way and kind of have learning progress that so far we haven't seen tail off, which is exciting. So now what I want to do is focus on pillar 2 and get to the main event of the talk. And that is going to be work into learning to continually learn, which was done with these fantastic collaborators here from all of these institutions. So thank you to all of them. So I think that everybody in this workshop knows about catastrophic forgetting. It's an Achilles heel of machine learning. For those who are watching this video that aren't familiar, the general idea is that all machine learning systems so far that we have built suffer from catastrophic forgetting, which is to say when they're in sequential learning, when they have to learn one task and then a second task, first they'll learn task A, but then while they're learning task B, they will do so by overwriting and completely forgetting everything they knew about task A. And that's why they forget catastrophically. In contrast, animals, including humans, forget more gradually. For example, I have not played volleyball in about 10 years. But I guarantee you that if I went to the court right now, I'd have to knock the rust off. But more or less, I would pick up where I left off at my skill level, and then I would be able to build upon that skill level. And we must solve catastrophic forgetting if we want truly general AI out there in the world with us that's continuously learning a variety of tasks. Imagine a robot in your home. You want it to learn all these different things that you want it to do in your home, and you don't want each time you teach it something new that it forgets everything else you've taught it in the past. So there have been many solutions to catastrophic forgetting proposed over the year. I would say that almost all of them are in the manual path. And here are some of them. And all of them kind of work a little bit in the domains where they have been tested. But the idea is that they haven't solved the problem by a long shot. And they're also kind of in this spirit where somebody had an idea. I think that this might help, and they kind of created an auxiliary law. So they built some machinery, and they tested it, and it works a little bit. And that's why I call them all in the manual path. I want to highlight this one here, which is sparse representations. People thought, oh, it really would be helpful for catastrophic forgetting if neural representations were sparse. But they didn't know how to get optimally sparse representations in terms of catastrophic forgetting, so they just stick it in auxiliary loss. It's like solve the problem and also try to make your representation sparse, and here's a hyperparameter that trades off between these two desiderata. And what we'll see later is that that approach isn't as good as just meta-learning the solution. So the frequent path in the manual path, as I was just mentioning in the example of sparse representations, is instead of optimizing for what you want, which is learning without forgetting, we have to optimize for something else and hope we get that learning without forgetting. For example, optimize for sparse representations, as opposed to letting the system learn whether or not it should develop sparse representations on its own, because that's useful for the overall goal. So the meta-learning philosophy is just that. We're going to say, what I want you to do is learn without forgetting, and machine learning can figure out all of its own techniques for how to accomplish that goal. So the hypothesis here, which is a sad one for us, but it's basically the bitter lesson from Rich Sutton, is that we're not smart enough to outsmart machine learning. That in the end, the solutions that really work well are those that let machine learning kind of do the heavy lifting and let and scale and take advantage of increasing amounts of compute. So the proposal here is to use meta-learning to learn to continually learn. We're going to learn a sequence of tasks, and then at the end, we're going to ask machine learning to be good at all of those tasks, not just the last one it saw. So if you look at meta-learning algorithms, there's two major camps. The first one is in the mammal style, or the hypergradient style, which is that you meta-learn a good initial set of weights, and then you later will subject those to SGD, and good things will happen. The other camp is that you meta-learn inside of a recurrent neural network, and the recurrent neural network creates its own internal learning algorithm inside of itself, which is the Jane Wang learning to reinforcement learn, or RL squared style. Which was showcased very well by the Rubik's Cube work at OpenAI. The work in this talk is going to focus on the first camp, although I actually think both camps are very promising, and we've experimented with both in our previous work. So here's the general idea behind mammal. You're going to have an initial weight vector theta, which was theta 1 on the left there. And then you're going to start a learning process, which is the first blue box, that's going to take a bunch of inner loop steps, which is that superscript, step 1, theta, step 2, all the way to step n. And then at the end of those n steps, you're going to evaluate that final set of weights, which is theta n1, on some loss function, your meta loss function there, which is, how well did you walk, for example. And then you differentiate back all the way through that entire blue box to that initial theta 1, and you say, how could we change the weights of this theta such that next time we run this entire inner loop process, at the end, we're better off. And you get the gradient of that, and you take that step, and that then gives you theta 2. So now the weight vector will be slightly better vis-a-vis the meta loss function the next time you run it, and then you keep doing that process over and over again. And we call that meta training, which is the terminology right there. So within meta training, it's useful to carve out two different phases. First, you have the meta training, which were those inner loop steps that you took. And then you have the meta training testing, which is you evaluate it to get that meta loss function that you're going to want to optimize against. Then after you do all of that, so you go from theta 1 to theta 2 all the way to theta m for all of the different m steps you took in meta training, now you'll switch to meta testing. So you will take this new weight vector you have, theta m, which is the result of your meta training, but now we have to see how good it is. But because we're testing for its ability to learn, it's a meta learning algorithm, that we need to, in order to test it, we need to have it learn for a little while and then evaluate how well it learned the stuff we just asked it to learn. So when we let it learn for a little while, that's meta test training, and that's this big blue box at the bottom here. So we will give it some new task, new challenge, let it take a couple steps of learning, including taking SGD updates based on the reward function of the environment or the labels, etc. And then after we let it learn for a while, then we'll switch to meta testing, where we will evaluate how well that theta m did on the challenge that it just learned. Okay, that's a lot of jargon, but I think actually setting up those semantics helps for the rest of the talk and for thinking about meta learning in general. Okay, so now when we switch to meta learning for continual learning, we have to make it even more complicated, but only slightly. And what we're going to do now is we are going to, within the inner loop of each inner loop training, you are not just going to take different steps of learning, but you're going to do sequential learning. So you're going to do task 1, you're going to take k steps of learning on that, then switch to task 2, k steps of learning on that, all the way up to task t. And then after you've learned all of those tasks in order, now we're going to evaluate you, and the meta loss is going to be how well did you do, not just on the last task, task T, but how well did you do on all of the tasks you just saw during learning, which means you have to have learned without forgetting, because you have to be good on the final, on all the tasks at the end. So then we will differentiate back through all of that and find an initial weight vector such that the next time we'll do better at learning through that whole process, and at the end being better on all of them. So we were originally working on this for a little while, actually, trying to meta learn the solution to catastrophic forgetting. And a lot of the stuff that we were trying wasn't working very well. And then I saw a talk by Martha White on this work done by Javid and White that was presented at Neurops in 2019, originally called MRCL and now called OML, or Online Aware Meta Learning. And their work was in the same style of trying to meta learn the solution to catastrophic forgetting, except it worked a lot better than what we had at the time. So we were very inspired by it. So we built off of a lot of their design choices, algorithmic choices, and their code, and ultimately ended up improving upon this technique. So I want to give a lot of credit to them. So the way that OML works is that they are going to take a certain network. Here we go. This is a network that's solving omniglot. And they have two chunks of the network. They separate the network into the representation learning network, which is blue, and the prediction learning network, which is red. And the idea is that during meta learning, they're going to train both of these. But at meta testing, they're going to freeze the blue and train the red with normal SGD. And so the challenge here is that meta learning has to learn a representation blue such that when SGD is learning on top of it, the entire system learns without forgetting. Specifically, the red layers have to learn without forgetting. What they found is that this performs very well. So after sequentially training on 150 classes of omniglot, which is a huge amount of classes historically for continual learning research, it was able to still remember how to do well on 97% of the meta test training set. So during meta testing, the examples you show it during meta test training, it can basically learn and memorize all of those. So it's near perfect memorization. However, it didn't do as well, though it still did impressive at meta test testing. So now it has to generalize to new instances of those classes it just saw during meta test training. And it got 63%, which is still pretty impressive, but not nearly as good as on the meta test training set. Also of interest is that it learned on its own sparsity. It learned to have sparse neural representations, which is really interesting and really validates kind of the vision of the meta learning approach. But it actually did it better than attempts to try to encourage sparsity manually. So here in the top row, you can see OML, and each one of the columns is a different image from the meta testing set. And what you see is that when you pass that image through the network, most of the neurons are quiet. Only a few of the neurons are used. So it produced a pretty sparse representation. But if you look all the way to the right, on average across the whole data set, it's using all of its neurons. In fact, there are no dead neurons in the representation. In contrast, if you look in the second row, what you see is that when you encourage sparsity directly via an auxiliary objective, you do get sparsity per sample, but you also, on average, see that many of the neurons have never been used. It's like an over-eager student that said, oh, you want me to have a sparse representation, so I'll just like shut down as much stuff as I can all over the place. It didn't actually know what you really wanted, which was have just enough sparsity or an intelligent way of being sparse to help in terms of catastrophic forgetting. And so it had a lot of dead neurons, and it ultimately didn't perform very well on the task. If you do normal deep learning, which is the bottom row, after you pre-train on some stuff and then you do normal FGD, you can see the neural representations are not as sparse per image, and on average, it's using the whole network, and that's actually why you get catastrophic forgetting, because it's not being sparse. Okay, so sorry about that. OML gets a lot right, but it's ultimately still subject to the tyranny of SGD, which was not optimized for continual learning. So it has this nice representation, but then at inference time, the red network is basically trying to learn via catastrophic, including kind of at all costs, and doing, it'll therefore, basically it wants to learn and forget. It wants to learn the new thing, it doesn't care about the old thing. And so these two networks are kind of warring with each other. And so the best that this system can do is has to find a blue network that is kind of as resistant as possible to the corrupting influence of SGD on the red network at inference time. So we wanted to see if we can do better. So what we propose is to allow control over SGD during inference by meta-learning something that can modulate SGD via what we call neuromodulation. So neuromodulation is something that happens in the brain, and there are many flavors of it, but the neuroevolution community long ago took inspiration from neuromodulation to start experimenting with meta-learning techniques decades ago, in which certain neurons in the network could modulate the learning of other neurons in the network and turn learning on and off in those neurons. So in a cartoon example, you could have a chess playing detector, something that detects when you're playing chess, and then it could turn learning on only in the chess playing part of the network while you're playing chess and off everywhere else, and then do the same thing for volleyball. And then at the end, you could have a volleyball and a chess playing network that did not interfere with each other during learning. So Andreas, I told you, has done a lot of pioneering work in this vein. And my lab followed up on this idea, but applied it for the first time to catastrophic forgetting. And what we found is on very small networks, on very simple problems, what we could do is that we could come up with neural networks that use neuromodulation to perfectly solve catastrophic forgetting, including turning learning on exactly in the right weights at the right time to protect against catastrophic forgetting. And so what we wanted to do in this work is we wanted to scale that up to deep learning. And we started to do that. And it wasn't really working very well. And Sean Ballou, the first author of this work, had this insight, which is that maybe the problem here is that we were only modulating the learning. We were not modulating the forward pass of the network. So if you think about it, if you have a volleyball playing network and a chess playing network, and they're both kind of fighting for control of your muscles, when either task is being performed, then you get a lot of crosstalk, and your performance isn't very good. And so what Sean came up with is the idea is that we would change neuromodulation such that it would gate the forward pass of learning, and that would therefore not only eliminate that crosstalk when either task is being performed, but it also indirectly allows the network to control the backward pass because it affects the gradients and the backward flow. And so that led us to this algorithm that we call a neuromodulated meta-learning algorithm, or ANML. And the idea here is that we're going to have a normal network, a red network, that learns just via normal SGD. But we're also going to have kind of a sister network on the side, which is a neuromodulatory network. It also sees the data coming in, and as a function of that data, like if we're playing chess or we're playing volleyball or we're looking at this particular type of character, it will send out an activation mask, which will be multiplied via element-wise multiplication towards one of the layers of the red network, or all of the layers. That's a design choice. In our case, it's just the penultimate layer. And so the blue network is to modulate the activations of, in our case, the penultimate or the second to last layer, the last layer of the red network. So in normal deep learning, you have inference everywhere, a forward pass everywhere in the network, and therefore you get learning everywhere in the network. And that's why you get catastrophic forgetting, because all knowledge is being cannibalized and overwritten to learn the task that's currently being learned. In ANML, in contrast, the forward pass is gated, and that then affects the gradient flow backwards. So any neurons that weren't used won't have gradients flow back through them. The domain here, following on the work of OML by Javid and White, is omniglot. So each type of character is its own class. So the first character is the first column here, and that is, you'll see a bunch of instances of that in a kind of a training set, and then you have a test set of held out characters, which you can see after the ... And then you'll go on to the next character, and then the next character, and the next character. So ideally what we would do is we would differentiate, we would have the inner loop be all 600 tasks of omniglot to really test the limits of the system. And we would differentiate after showing 600 tasks in a row, we would evaluate how performance did on all 600 tasks, and you differentiate back through all 600 of those tasks. Unfortunately, current meta-learning algorithms are not stable enough to go through that many sequential tasks. So one of the ingenious ideas of Javid and White's OML work was that they came up with a really brilliant approximation of that loss, which is quite simple, which is just that you learn on the next task in the series, and then you test how well did you do on that task you just learned, and a random sampling of previous things that you've been asked to learn, which approximates how well you're learning without forgetting all of the stuff that you have learned. And so every new task, you do that. You take a task, you learn a new task, and then you calculate performance on a held out set of characters from that task, as well as previously seen characters from previous tasks, and that's what you take a gradient step on. So here it is in pictures. You're going to each inner loop, you're going to see, you start with theta 0, and you're going to see a character, take a gradient step, see a character, take a gradient step. You're going to do that, for example, for 20 different characters. And then what you're going to do at the end of that is you're going to say, okay, how well did you do on those characters or held out examples of those characters? And how well do you do on previously seen characters from the meta training set? And then you differentiate all the way back up to that theta vector to say, what should that theta vector have been, such that at the end I do better on that entire challenge. And then you change to a new character and you do the same thing. Here's what that looks like for OML, where they're going to train the blue network and ultimately not freeze that and then allow the red network to learn on top of it. And for ANML, you've got these two side-by-side sister networks. One quick note is that we found that during meta testing, it actually does help even for ANML to freeze the kind of representation layers of that red network, although it wasn't essential. You can see our paper for the details of that. The results I show have that feature enabled. So now we'll switch to meta testing. At meta testing, what you're going to do is you're going to take entirely new types of characters, so new classes of characters you never saw during meta training. And first, you're going to do meta test training on them. So you're going to give it a couple of examples of that character and take inner loop SGD steps on that. And then you can evaluate it in two ways. So after 15 versions of this new character, we'll stop and we'll say, first of all, how well did you do on those 15 characters? We call that meta test training accuracy. That's in orange. And then we'll also test you on 5 held out examples of that character class. That's meta test training. So that's how well did you generalize? How well did you learn in a way that will generalize to held out examples of that character? And that's in green. And what you'll see is that we're slowly building up this plot here. And over time, after the end of, say, 200 characters, we can look at how well the network did on both meta test training and meta test testing. So I want to remind you before we look at results that continual learning is very hard. In normal deep learning, there's two things that help you. One is you have IID sampling, so you have random sampling from the entire data set. It's not sequential, and that means you can't have catastrophic forgetting. But you also get multiple passes through the data. In continual learning, you have sequential data, so you can suffer from catastrophic forgetting, and you only get one pass through the data. And we're going to show results on that type of challenging situation. So if we look at the results, what we can see is that, first of all, let's look at red. That's normal deep learning. You just train on the meta test training set and evaluate on both. And what you see is that the network basically, after training on a couple classes, it pretty much forgets how to do well on all of the classes, except for kind of the last one that it saw. And so performance on average across everything that it's seen so far is abysmal. It basically bounces along 0. If you pre-train on all the data from meta training and then start the network there, but still do normal deep learning on the meta test set, you have a little bit of a head start. That's why purple is better than red. But basically, quickly, it performs terribly on average across all of the tasks that it's seen. So for example, once it's seen 200 tasks, by the end of that training, on average, it's terrible across all of them. It's only really good at the ones toward the end. OML is in orange, and you can see it's much, much, much better across the board, but it starts to fall off in performance around 150, 200 classes, which is why you see the line go down. We actually were able to find an architectural change to OML that made it perform much better, and so we reported that. That's in the green line, and that is instead of freezing just the last two, instead of freezing all but the last two layers, you freeze all but the last one layer, so you only train one layer, and that was much more resistant to forgetting, which is the green line that you see here. ANML is slightly better than the green line, but the difference there is relatively small. Where the difference really pops out, though, is in meta test training. So on the left, it was kind of like when you saw new data, how well did you memorize it? The plot on the right is when you were trained on new data, how well did you then generalize to other examples of the classes that you just trained on? And here you can see this massive gap between ANML and even the best version of OML, and that's consistent kind of across the number of classes. And so what you can see, first of all, is the results are very impressive. You can train on 600 classes sequentially and still do pretty well on all of them on average after 600 classes. And the rate of degradation is really not that bad. And also you can see the large performance gap between ANML and OML, kind of demonstrating the benefit of this neuromodulatory approach to meta-learning the solution to this problem, which underscores that having kind of different materials in our system while we're meta-learning can really help. And so research into better architectures and better building blocks for machine learning will help as we're trying to meta-learn the solutions to all of our challenges in machine learning. One thing you can do also, which is really interesting, is that you can kind of compare the performance between the sequential case with one pass through the data and the IID case with one pass through the data. And that effectively isolates the effect of catastrophic forgetting. And so that allows us to see how much is catastrophic forgetting a problem in these results, with these algorithms. And what you can see is that if you look at training from scratch, which is normal deep learning, you get a 99% performance drop between having the data seen in a random order versus a sequential order, which is like, that is why catastrophic forgetting is such a problem in deep learning. Even with pre-training, you still see a massive drop of 67%. OML made a substantial dent in this drop, down to 47%. But ANML, in contrast, really sees very, very little drop between the IID case and the sequential case, which is to say that for this particular task, ANML has mostly eliminated catastrophic forgetting. It's just kind of making a marginal difference in performance. The performance delta between its results and other state-of-the-art results on OmniGlot is due to sample efficiency and other issues with only having one pass through the data. But it's quite nice and promising that you've almost entirely solved catastrophic forgetting on this problem. Another interesting thing is, like OML, ANML, it did learn, it meta-learned to have sparse representations, but ones that are better, again, than when you try to do that via an auxiliary loss. So here is the same basic analysis. The columns are 3 different random images from the meta-test test set. You can see that after you do the activation, the gating, which is the final row, the bottom row, it's very sparse, instance by instance, but on average across the data set, it's being the entire representation, all the neurons are being efficiently used. And in fact, both OML and ANML have no dead neurons in their representation, whereas you get 14% dead neurons if you try to hand inject a manual auxiliary loss for sparsity. So the conclusions for ANML are that ANML can learn 600 sequential tasks and still perform pretty well on average across all of them after that, which is very impressive in terms of the history of continual learning and catastrophic forgetting research. It harnesses neuromodulation via this multiplicative gating to allow selective activation in the forward pass, and that indirectly controls the selective plasticity, what will do experience learning during the backward pass. It also learns on its own to produce sparse representations, but it's also probably learning many other secrets and tricks that we don't understand yet to solve continual learning. And as we increase the complexity of the task and the size of these networks and the diversity of data, it's probably going to do more and more and more things that we're not even aware of to solve the problem of continual learning, just as evolution did in our brains. So future work, obviously, we want to take this to more and harder domains. And then to take it to the higher level, to the overall conclusions for the talk, I think that both OML and ANML show the promise of meta-learning, the solution to catastrophic forgetting in particular, which is one of the main subjects of this workshop. But more importantly, it kind of validates this overall meta-learning philosophy that we should optimize for what we want, which is do well on this giant distribution of tasks and do well after you see many tasks sequentially. So let's start taking off the crutches from deep learning and asking it to solve the real problems in the wild that we want it to solve, and we can use meta-learning to solve those problems. It's also in line with this vision of AI generating algorithms, or AIGAs, which is that we should meta-learn the solution to the hardest challenges in AI and machine learning. And I think this work raises a question of kind of what other ML grand challenges can we apply this technique to? Here's just a small example. You could meta-learn to explore safely, to generalize well, to be robust to adversarial and fooling examples. You could meta-learn to infer causality, to conduct experiments in the world, figure out how it works, to model the world, to be creative and solve new problems you've never seen before, et cetera, et cetera, et cetera. And so I encourage all of you out there that are watching this video to think about what problems you'd like to solve with such a powerful tool, and how you set up a system so that you meta-learn the solution to that very challenging problem. So the final thing that I would say is that ANML has really increased my confidence that the AI generating algorithm path is going to be the fastest path to producing AGI and human level AI and very powerful forms of AI, because it really kind of shows that these problems that have eluded us for so long, like once we have enough sufficient compute and data and we set things up and we give it the right building blocks, then it can produce answers and solutions to this problem that are better than anything we've come up with before. And I don't see any reason why that isn't going to be the path to produce the most powerful forms of AI. So with that, I want to say thank you very much to all of my fantastic collaborators on ANML and all of the work that I mentioned today, as well as the organizers of this workshop, our funding sources, and the organizations that have paid us and allowed us to do this fantastic work, and all of you for your time and for listening. Thank you very much, and I look forward to any questions you might have.
So thank you, Jeff, very much for this captivating talk, as always. I think we can just start with the Slido question. And we've got a very popular question on Slido, and then we can open for maybe a question or two from the audience. So the question from Slido is, does meta-training violate CL desiderata as the meta-learning loss is trained with respect to all tasks? In other words, it performs multitask instead of continual learning.
That is an excellent question. So here, what I will say is that there's a distinction between what we want to produce in the end and how we get there. So you could say that continual learning, to truly satisfy the continual learning task, you have to train in a sequential manner the entire time. And, to some extent, I'm sympathetic with that. But ultimately, I think what we want as a continual learning community is something that itself can continually learn. And we don't care how we get there. And so if we cheat as much as we want during meta training or using any techniques, and we ultimately get this neural net or this artifact that can go out into the world and continually learn really well. And once it's doing that, which is like meta testing, then it learns a sequence of tasks in order and learns them all and does all the desiderata that we want of continual learning. That's totally fine, and that's fair game, and that's what we want. And so I can see a little bit that people are like, is how you get there not the full task? But remember, I would just keep our eyes on the prize. We're never probably going to, well, at least not with a meta-learning framework, you're not going to get to something that ultimately gets you right to the final thing. In the same sense that evolution produced the human mind, and that is general intelligence, and that's beautiful. And so if we wanted something that could be really powerful and it ultimately produced something like the human mind, I don't think we'd care at all how we got there. And that's how I feel about continual learning. So the rest is a little bit of semantics, but I would just encourage people to keep their eyes on the ultimate goal.
Thank you for this. So the next question is, can a meta-learned continual learning method generalize to tasks outside of the meta-training distribution?
Yeah, it's an excellent question. I think this is kind of a fundamental question for machine learning in general, and I don't think it gets that much different for meta learning, with one exception, and that is that if you have a really big distribution and you meta train on it, then in addition to learning the facts and the knowledge of that distribution, you also learn to learn. You get extremely good at the process of learning, of conducting experiments to figure out causality in your world, of exploring your world to find out what it is you should do in the world, of exploring safely. And in that sense, I do think there's a hope that meta learning will go way beyond what traditional machine learning can do in terms of out of sample performance and out of sample tasks, because it truly has learned to learn. And on that new task, you can go learn whatever it is there to learn. Now, that said, if the learning problem itself is way out of distribution, like if we were in a world where what you learn in this second, like those laws of physics no longer hold in like 20 seconds, then yeah, probably the system would be hosed, because there is no free lunch. And ultimately, you do learn on some subset, and you want to exploit and bake in priors with that subset to perform really well on that subset. However, I think that's a very extreme notion of being out of distribution. For all the kind of out of distribution that we really care about as a learning community, I think probably the meta learning approach is really sound and probably will do much better than traditional machine learning for the reason I just said. And the example is on Earth. You know, humans are really, really good out of distribution because we've trained on all of the Earth type problems, and we can generalize to wildly different problems that are still kind of within the distribution of things on Earth, where you have consistent physics and some of the priors of humanity. And it's that sense of out of distribution we want to get good on, and we'll never get good on the true no free lunch sense of the distribution. So my instincts are that it's worth the LM bet, because it's probably about as good as we could possibly hope for to train something that doesn't just know stuff, but knows how to learn stuff, and therefore can adapt really quickly to new situations.
So the next question is a very interesting one, and we're running short on time, so I'm going to just ask you for just a quick answer, if you don't mind.
Sure.
But it's a really interesting question. So the question is, if the meta-learning procedure enforces the inner loop update to SGD, something like MAML does, can it still be considered to be learning the learning algorithm, i.e. it's maybe like level 1 meta-learning?
Yeah. Honestly, MAML makes my head spin a little bit. I mean, the fact that you can constrain the inner loop learning algorithm to just be SGD, and that the initialization matters so much vis-a-vis the resulting properties of the entire system. I think I would have answered no to that question before a lot of the interesting results from MAML. And now we're realizing that there is this bizarrely magical property where you can find this initialization subjected to SGD, and then totally different and interestingly different things happen. And you can optimize that to do wonderful things. So I guess it's comes down to whether you consider the initialization as part of the learning algorithm. It's a bit of a semantic issue. I think MAML would force me to kind of shade towards yes, even though my core resists that. But yeah, I think each person can decide their own semantics there.
Yeah. All right. Once again, thank you so much for the talk and for being here with us today.
Thank you, everybody.